Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. So in the fluid kinematics, which we are discussing the last few lectures, the last lecture we discussed about the Reynolds transport theorem, then the conservation of mass, the continuity equation which we have derived based upon the integral form, and we have also seen that we can use either integral form of differential form. So today we will discuss about the say the linear motion deformation, and then rotational flow, and then we will go to the potential flows, and further we will see the application of the potential flow. So we can see here, say, linear motion deformation. So volumetric dilation rate, as we discussed in the last lecture, so it is the rate of change of volume per unit volume. So say del V, that means the V is the velocity vector. We can express this as del U by del X plus del V by del Y plus del W by del Z. So where U, V are the U, V and W are the velocity components in X, Y, Z direction. So as you can see here in this figure, if it is a 2D problem, so linear motion, with respect to linear motion and deformation, you can see that if U is the velocity here, then at a location at delta X away, the velocity will be U plus W by del X plus delta X, and V is the velocity in this direction here. Then the other, say at a distance delta Y, the velocity will be V plus delta V by delta Y. So like this we can see the linear motion with respect to fluid movement and then deformation. So here you can see that, say, with respect to the deformation, so the volumetric dilation rate is 0 for an incompressible fluid, so that we can see that the variation of velocity in the direction of velocity simply cause linear deformation for fluid element. Shape does not change. So that means the volumetric dilation rate is 0 since the fluid is incompressible, and then variation is only in the direction of the flow. That means the shape does not change. So that we can then cross derivatives such as del U by del Y only cause angular deformation. But if you take in the direction of flow like del U by del X, that means the velocity U is in the direction of X, and del U by del X is the deformation in the X direction, and if you take the velocity component in the Y direction, then if you take del V by del Y, or the velocity component in Z direction, del W by del Z. So all this linear, it is in the direction of the velocities are in the direction of the corresponding Cartesian coordinate, so that we can say that only linear motion takes place, there is no angular deformation. So with respect to this, say here we can say that say this del U by del X plus del V by del Y plus del W by del Z is the total volumetric dilation. So now this we will further elaborate in the case of angular motion and deformation. So if the velocity, if the dilation is in, or the change in velocity changes in the direction of that coordinate system itself, then it is only linear motion. But if it is in the other direction, say for example del, instead of del u by del x, if it is we are considering del u by del y, it will be an angular motion, or it may cause an angular motion or deformation. So rotation of fluid particles at certain velocity gradient, like u plus del u by del y or delta y. So here you can see that the changes in the other coordinate system. So u is in the direction of x, that means x is in this direction and velocity is also in that direction, and v is in the y direction. So but if the deformation is with respect to y, the deformation, the change in u is with respect to y, that means del u by del y. And say for two-dimensional problem, if the change in velocity of v is in the direction of x, or del v by del x, then we can see that there will be a rotation of fluid particle, and then a certain velocity gradient will be produced, so which may cause angular motion and deformation. So this aspect is very important when we see whether there is any rotation or if there is no rotation, that means rotational flow or irrotation flow. So whether there is any angular deformation takes place, that is very important, we have to see. Then based upon that only we can say that the flow is rotational or the flow is irrotational. So for example, if you take this fluid element, say which is in 2D, which we are considering, so delta x is the length of the fluid element and delta y is the width of the fluid element which we are considering. So initially the shape is, say, just like in a rectangular shape shown here, but due to angular deformation, that means there is the change of velocity in y direction for u, that means del u by del y, and velocity v in y direction changes with respect to x, or del v by del x. So then you can see that there is angular deformation takes place at the rate of delta here in this figure, and then the angular deformation is in this direction. So A is shifted to A dash and B is shifted to B dash, and then with respect to this we can say that there is say rotation, and the rotation rate is written, say, omega OA, that means the rotation of this fluid element with respect to this OA is omega OA is del V by del X, and the rotation of the fluid element with respect to OB, if here is this is the origin O, so omega OB is the rotation is del U by del Y. So if it is del U by del X or del V by del Y, then it is only linear motion, and there is no deformation takes place in the other direction as explained here. So but if the deformation is with respect to other axis, that means U is changing with respect to Y and V is changing with respect to X for a two-dimensional problem, then as explained here, so omega OA is del V by del X and omega OB is del U by del Y. So this rotation of the element, say about a z axis, if you consider z axis also, then the average of the angular velocities omega OA and omega OB of two mutually perpendicular lines OA and OB, we can write omega z is equal to half del V by del X minus, say, del U by del Y. So with respect to the angular deformation, say if this is x y and if this is z axis, so we can see that, say, this which we are considering, say if this is OA and this is OB, and then deformation takes place, and then say omega OA we have already seen here, omega OA is equal to del V by del X, and omega OB is equal to del U by del Y, and then here we can see that, say, omega z is, if it is omega z is the rotation of the element about z axis, and then we can write this omega z, which is the rotation about the perpendicular axis with respect to x and y, is obtained as half del V by del X minus del U by del Y. It is del U by del Y. So omega z is equal to half of del V by del X minus del U by del Y. So like this. Now the rotation we have defined in the direction of z, that means since the with respect to OA and OB in this figure we have found the rotation omega OA and omega OB, and so similarly like this we can derive the rotation of the elements in the x axis, that means omega x can be defined as half del w minus w by del y minus del v by del z, and then similarly the rotation of the element about y axis will be half del u by del z minus del w by del x. So now the rotation of the element, so finally the rotation vector for a rotational flow can be represented as omega is equal to, as shown in this slide, we can write omega is equal to omega x I. So with respect to the ijk triad, that means with respect to the xyz direction, if you define the unit vector ij and k, then the rotation vector can be written as omega bar is equal to omega xi plus omega yj plus omega zk, where I, j, k are the unit vectors in x, y, z direction, and omega x, omega y and omega z are the rotational components in x, y, z direction as defined earlier. So the rotation vector finally we can write as it is the half curl of the velocity vector written like this. So that is equal to half del cross v bar. So that is equal to half of, say with respect to ijk, del by del x, del by del y, del by del z of uv w. So it can be written in this vectorial notation like this, and then the rotation vector can be written as a curl of the velocity vector like this. So now with respect to this rotation vector, we can define a term called the vorticity, and this vorticity is related to the fluid particle rotation. So the vorticity can be defined as, so in the case of a rotational type of fluid, so the vorticity we can define as say as a psi. Vorticity psi is equal to 2 times say the omega vector. So this is equal to del cross v bar. So this is called the vorticity of the fluid movement. So for rotational flow we can define the vorticity as say 2 times of the rotational vector which is written here, or that is equal to del cross the velocity vector. So this is defined as the vorticity. So for rotational flow, determination of the rotation vector and vorticity is very important. So as we have defined the previous slide, so first we are starting with respect to a fluid element, and then we are giving some rotation to that, and say for example for the velocity change for in the x direction, u is with respect del u by del y and v is with respect del by del x, and like that we are taking, and then finally we are defining the rotational vector with respect to z axis as half of del v by del x minus del u by del y, and then the rotational vector rotation in the direction of x as half of del w by del y minus del v by del z, and finally the rotation in the y direction as half of del u by del z minus del w by del z, del w minus del x, and then finally the rotation vector is defined, and finally we are defining the vorticity with respect to this rotational vector as 2 times of omega bar or del cross v. So now with respect to this say wherever rotational flow is concerned, with respect to the rotation and the vorticity, we can also define another term called circulation. So circulation is defined as the line integral of the tangential component of velocity taken around a closed contour. So if you consider a closed contour like this, then the term circulation is defined as, say circulation is equal to capital gamma is equal to the integral vs ds. So with respect to this figure it is defined here. So we are considering say a closed contour, and then their circulation is defined as the line integral of the tangential component of the velocity taken. So the limiting value of circulation divided by the area of the closed contour is the as the area tends to 0 is the vorticity along an axis normal to the area. So with respect to circulation also we can define the vorticity. That means it is the limiting value of circulation divided by the area of the closed contour as the area tends to 0 is the vorticity along an axis normal to the area. So thus as far as rotational flow is concerned, the rotational say vectors omega x, omega y and omega z, and then the vorticity and then circulation are very important terms, and with respect to this only generally we will be describing the rotational fluid motion. So now say after this rotational flow, now we will discuss about the irrotational flow. So irrotational flow, that means say here now as we have seen in the previous slide. So here in the case of irrotational flow there is no scope for rotation. That means fluid is only in the direction of, say, the changes is only in the direction of the velocity changes takes place in the direction of x for velocity component u, and say in the direction of y for velocity component v, and in the direction of z for velocity component w. So irrotational flow is a flow where we can define this del cross v bar is equal to 0. So that means the rate of angular deformation or rate of shear strain, say here this omega gamma is del v by del x plus del u by del y. So this is to be, there is no rate of angular deformation, so rate of shear strain is to be neglected. So this tends to 0. So that is the rotational flow is defined where del cross v is equal to v bar is equal to 0. So for the rotational flow we can see that there is, we don't have to consider the rotational components like omega x, omega y, omega z as we have seen earlier. So for rotational flow the vorticity is 0 or del cross v is equal to 0. That means say we can say that, say if we consider the rotational component in z direction. So here all the rotational components are 0. So omega z is equal to 0. That means say half del v by del x minus del u by del y is equal to 0, or we can write say del v by del x is equal to del u by del y. So and similarly we can write with respect to omega x, omega y and omega z. So that means for irrotational flow we can write, so for irrotational flow, so omega x is equal to 0, omega y is equal to 0 and omega z is equal to 0. So this omega z is equal to 0, this gives say as we have defined omega z is half del v by del x minus del u by del y. So that gives, so this is equal to 0. That means we can write del v by del x is equal to del u by del y. So this other components like say as we have defined earlier, say if you can take the components, the omega x is equal to 0, that will give del w y by del y is equal to del v by del z. And similarly if we consider the component in the direction of omega y, so omega y is equal to 0 will give del u by del z is equal to del w by del x. So here for irrotational flow all the rotational components are zeros, so that we can write say del w by del y is equal to del v by del z, and then del v by del x is equal to del u by del y, and then del u by del z is equal to del w by del x. So like this we can define all the terms, say when omega x is equal to 0, del w by del y is equal to del v by del z. When omega y is equal to 0, say del u by del z is equal to del w by del x, and when when this omega z is equal to 0, del v by del x is equal to del u by del y. So that means all the vorticity components are 0. So now with respect to this, now we will just see one example with respect to this irrotational fluid flow. We will discuss a small example here. So here you can see that we want to see there is a two-dimensional flow. For here the example which we are going to discuss is irrotational flow. Example for irrotational flow. A fluid flow in two dimension can be expressed by the equation v bar is equal to xy I plus x square minus y square x square minus y square j. So this is 2D flow. So v bar is equal to xy I plus x square minus y square j. So we have to determine whether the flow is rotational or irrotational. So since the velocity vector is now defined as v bar is equal to xy I plus x square y square into j. So this is the velocity in two dimension. So u can be the velocity in x direction can be written as say u is equal to xy and then v is equal to x square minus y square. So here this is we are considering a two dimensional flow, so that w is equal to 0. So u is equal to xy, v is equal to x square minus y square and w is equal to 0. So now we will take each component of the, so we have already defined three rotational components, omega x, omega y and omega z. So as per our definition, omega x is equal to half del w by del y minus del v by del z is equal to, so since the flow we want to show whether the flow is rotational or irrotational. So to show that if it is totally irrotational, then all the components omega x, omega y and omega z should be 0. So for this particular problem is concerned, here you can see that the w is already 0 and then we don't consider z direction since z component is not there. So the velocity, the flow is in two dimensions, so that you can see that omega x is equal to half omega del w by del y minus del v by del z. So w is already 0, so this component will be 0 and del v by del z, since there is no variation with respect to z, so this will be also 0, so that we can show that omega x is equal to 0. So similarly we will now do it for omega y. So omega y as per our definition is omega y is equal to half del u by del z minus del w by del x. So here again say del u by del z, there is no change of velocity in the direction of z, so this also tends to 0 and w is already 0. So finally del omega y is equal to 0 and then the third component, the third rotational component omega z is defined as half of del v by del x minus del u by del y, so that we can write this is equal to, so here the v is as far as our definition is concerned, the u bar is equal to v bar is equal to xy I plus x square minus y square j. So and u is defined as 2xy and v is defined as x square minus y square, so that del v by del x, if you differentiate v with respect to x, so del v by del x we will get as say when we differentiate this will be 2x and then del u by del y will be again 2x. So half of del v by del x minus del u by del y will be half of 2x minus 2x, so that also is equal to 0. So that finally we can see that all the rotational component omega x, omega y and omega z are 0 and hence the flow is irrotational. So here now we have proved for the given velocity for two dimensional case, so we have shown that omega x is equal to 0, the rotational component omega x is equal to 0, omega y is equal to 0 and omega z is equal to 0, and hence we can conclude that the flow is irrotational flow. And then say for two dimensional flow field you can see that omega x and omega y are always 0, since say as per the definition say say for two-dimensional flow, w the velocity component in z direction w is equal to 0, and then say the velocity variation of v as per our definition here, velocity variation v with respect to z will be also 0. So for two-dimensional flow, omega x, and for omega x is equal to 0. So similarly with respect to omega the y direction, omega y, del w, since w is 0, del w by del x is already 0, and since there is no variation of u with respect to z, so del u by del z is also 0. So for two-dimensional flow, we can say that omega x, omega y are always 0, since u and v are not functions of z, and w is 0. So that finally, say for irrotational flow, for two-dimensional flow, we have to only check generally omega z is whether 0 or not. So if it is irrotation flow, then we can say that del v by del x is equal to del u by del y. So this is the observation for two-dimensional irrotational flow. So if it is flow is rotational, there will be some values for omega x, omega y, and omega z. So like this we can differentiate whether the given flow is rotational or irrotational, so depending upon the problem. So this is about the rotational flow and irrotational flow. So most of our, say when we discuss about the fluid kinematics, so it is important that we should determine whether the flow is rotational or irrotational, since there are certain changes as per the principles or the theories which we will be using. Whether if it is rotational flow, then it will be different, and if it is irrotational flow, it will be different. And for rotational flow, as we have seen, we have to determine the rotational flow component omega x, omega y, and omega z, and also we have to determine the vorticity and circulation. But as far as the rotational flow is concerned, we are dealing with only, say, the variation with respect to x, y, z direction with respect to del cross v is equal to 0, and then we can define the various terms as far as irrotational flow is concerned. So now, before going with respect to the rotational flow, further we will be discussing about the potential flow later. But before going to the potential flow, here we will discuss the differential form of the continuity equation. So we have already seen earlier that when we derive the Gavani equation, the fundamental Gavani equation, we can either use the differential approach or integral approach depending upon the problem concerned. So for the conservation of mass or the continuity equation, in the last lecture we have already discussed about the integral approach, how to derive the continuity equation, and then we have also investigated some problems related to the integral approach of the continuity equation. So here now we will discuss about the differential form of the continuity equation. So to derive the differential form of the continuity equation, let us consider a fluid element just like in the slide. So here x, y, z direction, the velocities are u, v, and w, and so let us consider fluid element of size delta x by delta y by delta z. So with respect to x, y, z direction, so let the velocity be u, v, and w. So with respect to this, say, face of the cubic element which you are considering, so on this phase of the flow with respect to the fluid flow which you are considering, so on the left hand side the velocity, let it be rho u minus del rho u by del x into delta x by 2 into delta y into delta z, and then other side it will be rho u plus delta rho u by delta x into delta x by 2 into delta y into delta z. So now we are considering the x direction. So similarly for y direction, z direction also we can write, and then finally we can find the net rate of mass outflow in x, y, z direction. So if we consider the net rate of mass outflow in the x direction, we can write del rho u by del x into delta x into delta y into delta z as far as the fluid element which we considered here. So the rate of change of flow, or what is the possible outflow with respect to this the elemental, the control volume which we are considering, we can write net rate of flow will be is equal to del rho u by del x into delta x, delta y, delta z, and then net rate of mass flow in y direction can be written as del rho v by del y into delta x, delta y, delta z, and similarly in the z direction we can write with respect to the velocity component w del rho w by del z into delta x, delta y, delta z. So finally, with respect to the x, y, z direction, we can add all this the net rate of mass flow we can write as del rho u by del x plus del rho v by del y plus del rho w by del z multiplied by delta x, delta y into delta z. So with respect to this, now for the system concerned or for the control volume concerned, so now the mass is conserved, so that we can say that now using the equation d, the total derivative of the mass of the system dm of the system by dt is equal to, should be equal to 0, since the with respect to the conservation of mass the rate of change, total rate of change should be 0. So dm by dt is equal to 0. So now if we write with respect to the our earlier formulation, so these variations we have to consider with respect to time, that is del rho by del t, and then with respect to the xyz changes which we have discussed in the previous slide. So finally, with respect to dm by dt is equal to 0 can be written as del rho by del t plus del rho u by del x plus del rho v by del y plus del rho w by del z is equal to 0. So this is called the continuity equation in the differential form. So this is one of the fundamental equation of fluid mechanics. This is valid for steady, unsteady, compressible or incompressible flow. So this is the final. This is finally the continuity equation using the differential form of the formulation derived based upon the conservation of mass principle. So if the flow is say the fluid is incompressible, then we can see that there is no change with respect to rho, the density. So that density, this rho can be taken out and can be no need to consider. So that there is no change with respect to time or with respect to space. So for incompressible fluids, incompressible liquid, we can write del u by del x plus del v by del y plus del w by del z is equal to 0. So this is the differential form of the continuity equation, or the differential form of the conservation of mass as far as incompressible fluid is concerned. So del u by del x plus del v by del y plus del w by del z is equal to 0 at any point of the fluid which we are considering in for the particular domain which we are dealing with. So earlier we have seen the continuity equation based upon the conservation of mass for with respect to integral approach. There we have shown that a1 v1 is equal to a2 v2, where where a1 and so if you consider a system like this, say a fluid flow between section 1 and 2. So with respect to the integral approach, there if a1 is the cross sectional area at section 1 and a2 is the cross sectional area at section 2, and v1 is the velocity of flow at section 1 and v2 is the velocity of flow at section 2. Then with respect to the continuity, with respect to the conservation of mass based upon the integral approach, we have seen that a1 v1 is equal to a2 v2. And then here, as we are derived, so with respect to the differential approach, we can say if it is 2D flow, then we can write del u by del x plus del v by del y is equal to 0, or if it is 3D flow, as we have already derived here, it is del u by del x plus del v by del y plus del w by del z is equal to 0. So this is the continuity equation in the differential form. So the same continuity equation, if you consider, say sometimes we have to deal with the polar coordinate system or cylindrical coordinate system in terms of say the radial direction r and theta and z. So in that case the continuity equation can be derived as shown in this slide. So the velocity component can be written as, say, v bar is equal to vr unit vector er plus v theta unit vector e theta plus vz unit vector ez. So here this er, e theta and ez are the unit vectors with respect to r theta and z, and r theta z are the directions. So where theta is the angle and r is the radial direction and z is the vertical direction. So corresponding to this, as we have derived earlier in the Cartesian coordinate system, we can derive the continuity equation in the cylindrical polar coordinate system as, say, the final equation is del rho by del t plus 1 by r del r rho vr by del r plus 1 by r del rho v theta by del theta plus del rho vz by del z is equal to 0. So as we have seen earlier, for the incompressible fluid there is no change with respect to density rho. So we can write this equation as 1 by r del r vr by del r plus 1 by r del v theta by del theta plus del vz by del z is equal to 0. So when we are solving some particular problems where a cylindrical coordinate system should be used, say for example flow in a cylinder or in a pipe flow, if it is to be considered the cylindrical or polar coordinate system, then we can use this kind of continuity equation which is derived here for general equation and for the incompressible fluid. So now with respect to this continuity equation, we will just discuss one problem. So the problem here is say an example for the continuity equation in the differential form. So for fluid flow in an open channel, we want to derive for unsteady flow in a prismatic open channel. We want to show that the continuity equation can be expressed as del q by del x plus t into del t into say we want to prove that del y by del t. So this is del y by del t, del q by del x plus t into del y by del t is equal to 0. So where t is the top width of the channel which is considered, q is the discharge at time t, and x and y are the directions as shown in this figure. So we want to derive the unsteady flow equation, or we want to show that if q is the discharge flowing through a channel, we want to show that del q by del x plus t into del y by del t is equal to 0 for with respect to the continuity equation. So let us consider the open channel flow which is in the prismatic channel. So the flow depth is y and the area of cross section is a and top width is t as shown in this figure, and then let us consider a small strip like dA is equal to t into dy of depth y, and then let us consider two sections in the open channel at AA and at BB. So here the discharge entering at section AA is Q1 and discharge passing through at section BB is Q2, and at time t this the depth of flow is y, and then say that it is changing at delta t, there is a change of flow, and now we are considering the section between AA and BB at distance delta x as shown in this figure. So now from the figure which we have seen here, so from this figure we can write the flow between section AA and BB. Let us assume this discharge Q2 is greater than Q1 at any instant of time t. So Q2 minus Q1 we can write as the change of discharge rate between section AA and section BB. So Q2 minus Q1 is equal to del Q by del x into delta x. So we are considering now a time step delta t. So at delta t, volume rate of excess outflow over inflow can be represented as del q by del x into delta x into delta t. So delta t is a time step and delta x is the distance between section A and BB. So the volume rate of excess outflow over inflow is del q by del x into delta x into delta t, and then the water surface drop, say as shown in this figure, the water surface drop delta y can be written as delta y is equal to del y by del t into delta t, and finally the decrease in storage between AA and BB can be written as minus delta S is equal to minus delta A into delta x. So this is equal to minus t into delta y into delta x, as obvious from this figure here. So this is equal to minus t del y by del t into delta t into delta x. So the decrease in storage between AA we can write as minus delta S is equal to minus delta into delta x, that is equal to minus t into del y by del t into delta t into delta x. Now by continuity equation which we have derived by the conservation of mass, the decrease in storage between AA should be equal to, say, this change in storage, say, which is described here, that means volume rate of excess outflow over inflow. So we can equate both this, so that we can finally write as del q by del x into delta x delta t is equal to minus t del y by del t into delta t multiplied by delta x. So delta x delta t will be cancelled, and finally we can obtain del q by del x plus t into del y by del t is equal to 0, which is what we are asked to show. So for unsteady flow in prismatic channel, here we have shown that del q by del x, that means the discharge rate change of discharge with respect to x, del q by del x plus t into the top width by del y, that means change of depth with respect to time, del y by del t, that is equal to 0. So that is the continuity equation differential form for open channel flow. So that we have shown that del q by del x is equal to t into del y by del t is equal to 0. So this is the continuity equation for open channel flow. So we will, before proceeding to the potential flow, we will solve one more example with respect to the continuity equation, the differential form which we have derived here. So here the problem is for a steady state incompressible fluid flow. For a steady state incompressible fluid flow, the velocity components are given as u is equal to 2x square plus 3y square plus z square. So if x is in this direction, y and z is defined here. So u is equal to the velocity component, u is defined as 2x square plus 3y square plus z square, and the velocity component v is defined as 3xy plus 2yz plus 5z. So we have to determine the w component of the velocity. So this u is in this direction, v is in the y direction, and w is in the z direction. So here with respect to u and v components are given. So with respect to continuity equation, we want to determine the velocity component w. So from the continuity equation which we have derived, we can write del u by del x plus del v by del y plus del w by del z is equal to 0. So now with respect to, since u is given in this problem, u is given as 2x square plus 3y square plus z square. So that we can write del u by del x is equal to, if you differentiate this function, we will get del u by del x is equal to 4x, and it is also given v is equal to 3xy plus 2yz plus 5z. So that we can write del v by del y is equal to 3x plus 2z. So now from the continuity equation, here we have written del v u by del x plus del v by del y plus del w by del z is equal to 0. So we can substitute for del u by del x and del v by del y, so that we can obtain del w by del z. So after substitution for del u by del x and del v by del y, we will get del w by del z is equal to minus del u by del x minus del v by del y. So this is equal to minus 4x minus 3x minus 2z. So del w by del z is equal to minus 7x minus 2z. So now we want to determine the velocity component in the z direction w. So to get w, we can integrate this del w by del z. So on integration we get minus 7xz minus z square plus a constant fxy. So this fxy we can determine from the other conditions which will be given for the problem. So now from this, say the continuity equation differential form is used to determine the one component, the z component of the velocity, if the velocity component in the x and y directions are given. So like this we can use this continuity equation, the differential form, for various problems as one of the fundamental equation. So now we have seen the rotational flow and the continuity equation in the differential form. So now we will go to the potential flows. We will discuss some aspect of the potential flow. So before going to the potential flow, let us see what is a velocity potential. So generally, as far as fluid mechanics is concerned, to say we can, if you define terms like velocity, potential, stream function, etc., this can be used to represent the fluid flow in many terms, especially in the fluid kinematics. So here we are going to define the velocity potential and then its various applications. So velocity potential is generally expressed as phi as a function of x, y, z and t. So in 3 dimension x, y, z and with respect to time. So this is the velocity potential is represented as phi, and it is defined. So the velocity potential is defined as, say, if the velocity component in x direction u is equal to del phi by del x, that means the variation of phi, the velocity potential with respect to x, and the velocity component in y direction, if you take the differential of say the velocity potential in y direction, that will give the velocity component in y direction, and the velocity component z direction, w is represented as the del phi by del z. So the velocity potential is defined such that the velocity in x, y, z direction, say if you consider the fluid flow, and here if x, y and z are the Cartesian coordinate system, and then the velocity in x direction is u, velocity in y direction is v, and velocity in z direction is w. So we are defining a term called velocity potential, which is varying with respect to x, y, z and t, such that this velocity variation in x direction u we can write as del phi by del x, and velocity variation in y direction we can write as del phi by del y, and velocity variation in z direction we can write as del phi by del z. So that is the way which we define this velocity potential. The consequence of irrotationality of the flow of fluid and can be defined for 3D flow. So we can also define another term called stream function, which is a consequence of conservation of mass restricted to 2D. So that we will be discussing later. So the velocity potential here phi is defined such that the velocity component in x, y, z direction, u, v and w can be defined as del phi by del x, del phi by del y and del phi by del z. So now if we use the continuity equation, the differential form of the continuity equation which we have just defined earlier, which we have derived earlier, so that for in 3D we have derived that del u by del x plus del v by del y plus del w plus del w by del z is equal to 0 for x, y and z direction. So now if we apply this, say we have also defined u is equal to del phi by del x, v is equal to del phi by del y and w is equal to del phi by del z. So we will substitute for this u, v, w in this equation of the continuity equation. So if you substitute here for u, v and w, so that we will get as del square phi by del x square plus del square phi by del y square plus del square phi by del z square. So that is equal to 0. So this equation is called the Laplace equation, represented as in this slide. Del square phi is equal to 0. It is a Laplace equation and it governs inviscid, incompressible, rotational flow field. So the potential this kind of flow is called potential flow, and the theory is related to this kind of flow is called potential flow theory, and the governing equation for this inviscid, or non-viscous incompressible fluid flow, irrotational inviscid incompressible and irrotational flow field is the Laplace equation defined as del square phi is equal to 0 as derived here. So this type of flow is called potential flow, and for this kind of flow we can have, say, if you consider any domain where we are considering the potential flow. So the given equation is del square phi is equal to 0, and then say for example if you consider the fluid the flow in a homogeneous isotropic aquifer system like this, so then we can have two types of boundary conditions. So now the given equation is defined and we can have two types of boundary conditions. The boundary conditions generally defined are one is the Dirichlet boundary condition, say Dirichlet boundary condition, which is also called the direct boundary condition. So here we can describe, say, phi, the potential phi is equal to phi 1 bar, and on this direction at this place we can phi is equal to phi 2 bar, and then another type of boundary condition we can also define del phi by del n is equal to, say, in this direction this is impermeable, so there is no flow, so here also del phi by del n is bar is equal to 0. So two types of boundary condition can be defined for this kind of problem. One is the Dirichlet boundary condition and then Neumann boundary condition, and sometimes also a mixed form boundary condition can be used. And now this the velocity is obtained from this expression from the potential which is defined from the Laplace equation, and then the pressure of flow can be obtained from the Bernoulli's equation, which we will be discussing later part. So for the potential flow, the velocity is obtained from the Laplace equation, and the pressure is obtained from the Bernoulli's equation. So potential flows, as we have defined, it is inviscid. This potential flow theory is used for inviscid, incompressible, and it is irrotation flow, and the flow fields are governed by the Laplace equation and called as potential flows, and the lines of constant potential is called the equipotential lines, and it forms the orthogonal grids with the streamlines to form a flow nets, which we will be discussing later. So with respect to the potential flow, we will just discuss a small example here. The potential flow for a 2D incompressible fluid flow, velocity components are given as u is equal to 4xy, v is equal to s square plus 2x square plus 2y square. We have to show that the velocity potential function exists, and we have to determine the velocity potential. So for this problem, say the potential phi exists for irrotational flow only. The condition is del v by del x is equal to del u by del y. So with respect to this, now we can show that, so u is equal to, u is given as 4xy, and if you differentiate with respect to y, del u by del y is equal to 4x with respect to when you differentiate, and this function v, when we differentiate, del v by del x is equal to again 4x, so that we can see that del v by del x is equal to del u by del y, so that flow is irrotation. And then as per the problem, we want to determine the first we have to show that velocity potential exists, and then we have to, since the flow is irrotational, the velocity potential exists, and then we have to determine the velocity potential. So by definition, u is defined as del phi by del x, and u is here defined as 4xy, and then phi is equal to, also is equal to x square y plus, say, phi is d phi by dx. So if we integrate this, we will get, say, here on integration we will get 2x square phi plus f1y, and then v is defined as s square plus 2x square minus 2y square, and which is equal to del phi by del y, or on integration of this function we will get phi is equal to s square y plus 2x square y minus 2 by 3 y cube plus f2x, and both solutions should be same, since phi is obtained with respect to x. Here phi is obtained as 2x square y plus f1y, and with respect to v we got phi is equal to this function. So now both solution should be same, since phi is same. So we can write 2x square y plus f1y is equal to s square y plus 2x square y minus 2 by 3 y cube f2x, or we can write f1y is equal to, we will get f1y is equal to s square y minus 2 by 3 y cube plus f2x. So to keep above expression valid for all values of y, we have to it should be f2x has to be constant in this equation, so that finally we can write the velocity potential phi is equal to s square y plus 2x square y minus 2 by 3 y cube plus constant. And since phi is the velocity potential constant and represent a family of lines, phi may be written without a constant, as finally phi can be written as s square y plus 2x square y minus 2 by 3 y cube. So like this, the definition of potential we can use to determine the velocity, or the velocity is given, we can determine the potential function, and this is valid. The potential flow theory is valid for inviscid, incompressible and irrotation flow, and the field are governed by Laplace equation, and the flows are called the potential flows. So further we will be discussing about this potential flows and related theories in the next lecture.